Hello everyone. Now that we have had some background about inference in multivariate normal distribution, we have to move to the next stage. So estimation is done. Now our job is to do testing. We know that entire purpose of statistics is going from sample to population, and if you want to go from sample to population, we do need testing a lot. So we know how to compute sample mean for given multivariate normal data. But using that sample mean, we want to guess something about population mean. And the very basic thing that we would try to do is, can this sample mean provide me sufficient enough evidence to conclude that population mean is in a certain range? That is what we always do. So today we are going to start with that testing part. So the first test that we are going to look into is likelihood ratio test for testing whether population mean is can have a certain given value mu naught. So my h naught is actually vector mu equal to mu naught. So mu naught is also a vector, but mu naught is a pre-specified vector. For example, if I am studying say a group of patients and I want to test whether their blood pressure levels are normal, so I can have their systolic blood pressure as say P1, diastolic blood pressure as say P2, and then I would be interested in testing whether mean of this means expectation of this P1 P2 is it equal to 120 80. Okay, this might be my interest. So in that case my 120 80 becomes mu naught. So how to proceed in such scenario? There are actually many different ways of testing this. Today we will be seeing one of those ways, which is done via likelihood ratio test. I think some of you might have done likelihood ratio test during BSc, or if not during the current inference course. So first let us try to recall what is meant by a likelihood ratio test, and for that first, what is likelihood? So we have seen this during maximum likelihood estimation also. What is likelihood? Likelihood gives you in some sense the probability that the given sample is generated for the values under consideration, from the values of parameters under consideration. So when I am performing likelihood ratio tests, I am supposed to compare two likelihoods via taking their ratio. Hence the name likelihood ratio test. The typical standard form for likelihood ratio test is the test statistic lambda is defined as supremum over theta in parameter space theta naught. This theta can be a vector or a scalar, L theta, upon supremum over theta in entire parameter space script theta, L theta. What does this mean? Let us first try to see what are the meanings of these notations. So my script theta is entire parameter space. So in the case of multivariate normal mean, my script theta will be p-dimensional Euclidean space, that is RP. Script theta naught is the restricted parameter space under H naught. So this is parameter space under H naught. Okay, so H naught can be anything. If my H naught is say mu is positive in case of univariate scenario, then my script theta naught becomes open 0 to infinity. So script theta naught is the restricted parameter space under H naught. So what does likelihood ratio do? Likelihood ratio says consider supremum of likelihood when that supremum is taken over the restricted parameter space and take ratio of that to the bigger one. So if my entire parameter space is this, so if this is my script theta, we know that script theta naught is going to be a subset of it. Okay, because H naught is part of the entire parameter space, so script theta naught is subset of this. So first we take supremum over this smaller region. So supremum over this smaller region, suppose that supremum is here. Okay, that supremum is this. Now we take supremum over entire region. There are two possibilities. If this value is highest over all others also, then supremum over entire region is also going to be this. But there is a good possibility that some value from this part is higher than this value. Okay, so likelihood value at some point from here is higher than this. In that case, the supremum would lie outside. So maybe this is my supremum. So what we try to do is, if at all this value is highest, then supremum over script theta naught and supremum over entire script theta would be exactly same. As a result, my lambda would be equal to 1. However, if they are different, what can I say about lambda? Can my lambda take any value, or can it take any positive value or something else? First of all, I am taking ratio of two likelihoods, and all of us know that likelihoods cannot be negative. So my lambda has to be greater than 0 or at most greater than or equal to 0. This much we know. So we saw one case that if script theta naught, if supremum over script theta naught is same as supremum over entire script theta, then we know that lambda is going to be 1. If that is not the case, means if supremum over script theta naught of likelihood is not equal to supremum over script theta entire theta, then what can I say? In that case, we know that this is not overall supremum. This is not overall supremum means this is less than this. So the supremum over entire parameter space has to be greater. As a result, my lambda will always be less than 1. So this would imply that lambda is less than 1. Hence, in general, my lambda is always between 0 and 1. It can never exceed 1. Therefore, likelihood ratio, when you are taking the ratio and in this setup, means the numerator parameter space is nested under the denominator parameter space, then lambda is always between 0 and 1. So if lambda is between 0 and 1, then which values are favorable to H0 and which values are not favorable to H0? So if H0 is true, means if the given data supports that H0, then in that case likelihood is likely to be high under H0. As a result, numerator is likely to be high under H0, because that is what meant by saying that given data supports H0, that is likelihood under H0 should be high. So in that case, lambda would be very close to 1. Okay, so therefore, if data support H0, then lambda will be very close to 1. Therefore, my rejection region in such type of LRTs, LRT is likelihood ratio test. So my rejection region in such type of LRTs is actually where lambda is very less than 1. Okay, so basically if lambda is close to 0, then in that case we will be concluding that H0 is wrong, because supremum under overall space is much higher than supremum under H0. Hence we would say that the current data do not support H0 much. Okay, so the important thing is here, lambda, very small value of lambda actually leads to rejection. Okay, now let us come to the actual problem at hand. So my current problem is I have O1, O2, On, each coming from p-variate normal distribution with mean mu, variance covariance matrix sigma, and their IID. Okay, O1, O2, On are IID observations coming from p-variate normal distribution with mean mu and variance covariance matrix sigma. My aim is to test H0 whether mu can be said to be mu naught. Okay, mu naught is some constant value in p-dimensional Euclidean space. Okay, My aim is to test whether mu takes a particular value mu naught. So in my likelihood ratio test, in the numerator I have to substitute mu naught, and in the denominator I can substitute usual MLE, that is going to be sample mean, that is O bar. Okay. Now mu naught fine, but what about sigma? I know that in the denominator my sigma hat will be CSSP matrix. That is known to me. But what would happen to sigma under H naught? So those things also need to be addressed. Just to make things more clear, let us first write down what is script theta. Script theta is collection of all mu and sigma such that mu is in Rp and sigma P cross P is symmetric positive definite matrix. Okay. Sigma P cross P is symmetric positive definite matrix. Script theta naught is mu naught sigma, where mu naught is that fixed value from Rp. So there is no scope of change in mu naught, and sigma is same. So sigma P cross P is symmetric positive definite matrix. There is no change in sigma. So when we say we want to maximize the likelihood under both these spaces, first I have to maximize under H naught, that is over script theta naught, and then over entire parameter space. Now I am going to give you some homework. So we know that MLE of mu under H naught will of course be mu naught. That is obvious because no other parameter value is allowed. My H naught allows only mu naught to be a possible value. So no question there. But the problem is, what would be MLE of sigma under H naught? So when I say under H naught, what is going to change? Instead of mu, we are going to substitute mu naught, and then we are going to maximize the log likelihood. So we have already studied maximization of log likelihood under overall setup when we were deriving MLEs. So you have to follow exact same things, and you have to find out MLE sigma naught hat. As I said, this is homework, so I'll just directly give you the answer. Sigma naught hat turns out to be summation I going from 1 to n y minus mu naught prime upon n. If you recall the univariate setup, you know that in the univariate setup, when population mean is known, estimate of sigma square is done by using similar technique, that is by replacing sample mean by the known value of the population mean. So this is exact equivalent of that, but as I said, I am not going to derive it here. This is your homework. Okay, try to derive sigma naught hat. Once you know this sigma naught hat, we are going to substitute this sigma naught hat in the likelihood, and of course mu naught hat in the likelihood to get the supremum of likelihood. So we know that in the first part there is only sigma naught, so no problems there. Exponential part is most crucial. So what is the exponential part? Exponential part is minus half y minus mu naught prime sigma inverse y minus mu naught. Okay, because we are substituting mu equal to mu naught, it will be this. So now let me substitute sigma naught in place of sigma. So this would become e raised to minus half y minus mu naught prime sigma naught hat inverse y minus mu naught. Now we will use the exact same ideas, that is y minus mu naught prime sigma inverse y minus mu naught is actually constant. So I can write it as trace of itself, and once I write it as trace, I can change the order. So this would become e raised to minus half I'll keep minus half outside, trace of, of course I'm forgetting summation. So summation I going from 1 to n is there, I going from 1 to n. Okay, I will take summation inside, I going from 1 to n, y minus mu naught prime sigma naught hat inverse y minus mu naught. Okay, so I will take the trace inside the summation, so I will have e raised to minus half summation I going from 1 to n, trace of y minus mu naught prime sigma naught hat inverse y minus mu naught. Since we know that inside trace order can be changed, so this becomes e raised to minus half summation I going from 1 to n, trace of sigma naught hat inverse y minus mu naught into y minus mu naught prime. Okay, now since trace itself is sum and I have a summation sum here, and both these are finite sums, so they can be interchanged, and sigma naught hat is free from this I, so it can be taken outside the sum. So I can rewrite this as e raised to minus half trace of sigma naught hat inverse sum over I going from 1 to n y minus mu naught into y minus mu naught prime. Okay, so this becomes e raised to minus half trace of sigma naught hat inverse, and this is nothing but sigma naught hat summation y minus, of course this upon n, so this is sigma naught hat times n. Okay, so I am left with n times identity matrix, and hence this becomes e raised to minus half trace of ni, where I is identity matrix of order p cross p, hence this is e raised to minus np by 2. So exactly like in the case of MLE, the exponential term here gets simplified a lot and it becomes only e raised to minus np by 2. Okay, so what I know now is supremum under script theta naught of log likelihood, where by theta I mean both mu sigma. Okay, so this supremum is 2 pi raised to minus np by 2 determinant of sigma naught raised to minus n by 2, okay, and e raised to minus np by 2. From the MLE proof, we already know that supremum over entire parameter space is going to be 2 pi raised to minus np by 2 sigma hat raised to minus n by 2 e raised to minus np by 2, because in that case also we know that the terms inside exponent get cancelled and we are left with identity matrix. So when I take ratio, this lambda is going to be sigma naught hat raised to minus n by 2 divided by determinant of sigma hat raised to minus n by 2. So I can rewrite this as determinant of sigma hat upon determinant of sigma naught hat raised to n by 2. I have changed the numerator to denominator and hence the sign of the power has been changed from negative to positive. We also know that sigma hat is s by n, so this can be written as determinant of s by n upon determinant of sigma naught hat whole raised to n by 2. Okay, everyone with me so far? Okay, now if I want to simplify this further, I would need to see what is the relationship between s by n and sigma naught. So let us try to do that. Let us try to find is there any relationship between S by n and sigma naught hat? So what I know is n sigma naught hat is sum over I going from 1 to n oi minus mu naught into oi minus mu naught prime. This much I know. Okay. So if I want to relate this to S, I should bring in O bar so that I'll have terms of the type oi minus O bar, and those are forming components of S. So I would have I going from 1 to n oi minus O bar plus O bar, because I can't just bring in something, I have to adjust for it, and oi minus O bar plus O bar minus mu naught prime. So let me try to simplify this. So this becomes I going from 1 to n. Again I would treat this as one term, second term, third term, fourth term, of course with primes. So my first term is oi minus O bar into oi minus O bar prime. Okay. Plus second term would be O bar minus mu naught is free from I, so I will keep it outside. O bar minus mu naught into summation oi minus O bar prime, I going from 1 to n, plus oi minus O bar summation I going from 1 to n into O bar minus mu naught prime, plus O bar minus mu naught into O bar minus mu naught prime. Okay. We can easily see that this is nothing but sum of deviations of observations from the sample mean. So this is going to be 0. Similarly, this is also going to be 0. This is anyway free from I, so it remains outside. So these two terms vanish. So I am left with summation oi minus O bar prime, which is nothing but S. So S plus, okay, actually this is n times because I am taking sum over n times. So n times O bar minus mu naught into O bar minus mu naught prime. Hence what I know is sigma naught hat is actually S by n plus this. Okay, so if you want, let me write. So sigma naught hat is actually S by n plus O bar minus mu naught into O bar minus mu naught prime. Okay. But we can't stop here, because ideally what we want is relationship between determinant of sigma naught hat and determinant of S by n. This is what we want. So for that we need some further simplification. We are going to use one result from linear algebra. Let me state that result. It's your homework again to find out the proof for that result. Okay, you don't have to write it here, you can use the result directly. So the result is this: let A be a matrix of order r cross r and B be a column vector of order r cross 1, and we are defining the new matrix C as A minus B, B prime and 1. Let us check the orders. A is r cross r, B is a column vector, so r cross 1, B prime will be 1 cross r, and 1 is scalar, actually 1 cross 1. So my C matrix is of order r plus 1 cross r plus 1. So linear algebra says that determinant of C can actually be written in two different ways, can be computed in two different ways. One way is determinant of A into, so determinant of A into 1 plus B prime A inverse B. That is one way. So this is written over here. And another way is determinant of A plus BB prime. Okay, because it's kind of like A into 1. So A plus BB prime. See, you know, both these plus signs are coming because there is a minus sign over here. So the minus sign from determinant is getting adjusted with this minus sign. So we will use this result. What I want is determinant of sigma naught hat. So determinant of sigma naught hat from this form can be written as determinant of S by n plus O bar minus mu naught into O bar minus mu naught prime. and this form is nothing but this second row. So if I put A equal to S by N and B equal to O minus mu, then this is exactly the same equation. So I know that this can be written in this way also. So that is what we will do. So we will write this as determinant of S by N coming from the first step over here into 1 plus O bar minus mu naught prime S by N inverse O bar minus mu naught. Okay. So this is what we have written over here. As a result, when I substitute this in my lambda likelihood ratio test statistic, my S by N, determinant of S by N, gets cancelled and I am left with only this term in the bracket and that too in the denominator. That is 1 plus O bar minus mu naught prime S by N inverse O bar minus mu naught. Okay. Now, we saw in the beginning that we reject H naught if lambda is very close to 0. So in this particular case, lambda being very close to 0 is equivalent to this being very large. Hence, we would reject H naught when this is very large. Now let us see if intuitively this makes sense. Yes, because if O bar minus mu naught prime S by N inverse O bar minus mu naught is very large, what does it mean? So this is kind of deviation of O bar from mu naught, right? This is deviation of O bar from mu naught. As a result, we are kind of having squared deviation of O bar from mu naught. So if that is large, then we would tend to reject H naught, which makes sense. That is, if sample mean is far away from the population mean under H naught, then we would say that H naught is probably wrong. So it should be rejected. And this comes up as a scaling factor. If you remember your t statistic from the univariate setup, this is equivalent to that. So in the univariate setup, we used to have x bar minus mu naught upon sigma s by root n. Okay, sigma by root n or s by root n. So this is something similar, except we are taking square of it. So x bar minus mu naught is getting squared, prime and this s by root n is also getting squared. The notation for s in univariate and s in multivariate are different, so you can't see the square, but it is basically that. Okay. Hence, it makes sense. So this LRT is giving intuitively correct result. That is, if the scaled deviation of O bar from mu naught is very high, then we tend to reject H naught. Okay. We are not going to go into the exact limit theory. Asymptotic limit theory says that minus 2 log lambda in case of LRT follows chi-square distribution with certain degrees of freedom, say k, where k comes from difference between dimensions of the two parameter space under H naught and overall. Difference between dimensions of two parameter spaces. So in this particular context, my minus 2 log lambda would actually be minus 2 log lambda would be n by 2 log of, if I take minus sign, then log of 1 plus O bar minus mu naught prime S by N inverse O bar minus mu naught. Okay. So 2 gets cancelled, minus sign gets cancelled. So I am left with n times log of 1 plus O bar minus mu naught prime S by N inverse O bar minus mu naught. And this would follow chi-square distribution with the difference between the two parameter spaces. So under H naught we estimated only sigma naught hat because mu naught was known. Whereas under overall setup we estimated both mu hat as well as sigma hat. So the sigma hat, number of unknowns in sigma hat and number of unknowns in sigma naught hat is exactly same. So they will cancel each other out. So I am left with additional p unknowns which were present in mu hat under overall setup. So this becomes chi-square with p degrees of freedom. So my likelihood ratio test statistic is actually this: n times log 1 plus O bar minus mu naught prime S by N inverse O bar minus mu naught we would reject it, and we would say under h0 its distribution is chi-square p. So we would reject if the cutoff is far away from chi-square p. And as I said, it makes sense. We would reject for large values here, large values of chi-square p. For lambda, we reject for small values obviously, but because we are multiplying by minus sign, the conclusion is reversed now. So large values of chi-square is same as large values of this. That is, the distance is large. Okay. So this was how to test mu equal to mu naught under using LRT. We are going to have few more results, but they will be based on Hotelling T-square, so I would reserve it for a separate lecture. So for now, let us stop here. Thank you.